This lecture we will look at stochastic vectors. This figure shows the monthly sales of red wine by Australian winemakers over a couple of years. And for some different reasons, you might be curious to predict how much wine will be consumed in the future, or maybe you are interested to see if their trends are the Australians drinking more wine, or is there a particular season when they drink more wine, or something like that. Say that you wish to model that. How would you be able to draw such conclusions, and what would be a reasonable way to predict how much wine that will be consumed? First of all, you should see then that there seems to be some kind of growing trend. So it seems like the Australians are drinking more and more wine. There is also a growing variability. You can sort of see that there is sort of a change in the data that's sort of having a wider and wider spread as time goes by. So there seems to be a different variation of how much wine is consumed. You can also see that there is a clear periodicity in the data. So there is typically a season, maybe it's the summer, that when they drink more wine, and then there is some season when they drink less wine. So of course, if you want to do that kind of prediction, you would want to take all these things into account. If you know that it is a summer coming on, you know that you should expect there to be more drinking, more wine consumed than if it is a winter, or the other way around, depending on which is which. So how would you go about dealing with that is what we will consider in this course, and we will look further at. But now we will begin by saying, well, if I have a measurement like this, I will consider it as being one realization of an n-dimensional stochastic variable, or a stochastic process we'll come to later on. But the difference here is small. So say that I have p measurements. This is a p-dimensional stochastic variable. I will just stack it into this capital X here, and I will say, okay, so now I have a measurement. This is one realization of the stochastic variable X, and this is what I have seen. And I would be curious to know, of course, what is the probability distribution of that variable. I will write out the probability distribution function, which is just then the probability that the different coefficients in my vector are different, the alpha 1, alpha 2, and so forth, just as in the two-dimensional case. Similarly, I will have partial derivatives with respect to all the different unknowns, alpha 1, alpha 2, and so forth, and I'll get the PDF, the probability density function, which tells me the probability mass, where is the likely occurrences. Of course, now it is in a p-dimensional space, but everything else works just the same as it was before. I would be curious in finding the mean of my stochastic variable. It's p-dimensional, yes, but that means that if I write out the mean of the stochastic variable x, the only thing is that I'm moving the expectation inside, so that it's expectation of each of the individual elements like this. If the expectation is just as it was before, it's the integral over the computational density. Of course, it is a p-dimensional distribution function now, but it's a p-dimensional integral, but we'll still just write it like this with vector notation. But it's exactly the same thing. You move the integral in and take an integral over each of the dimensions. So you have p different integrals, and then you just start integrating if you want to do that by hand. The notion of variance is now turning into the notion of a covariance matrix. So now it is the dependency of the different indices to each other that you construct into this p by q covariance matrix of the stochastic vectors x and y, which I'm taking the x minus its mean, y minus mean, and now I again notice that I have the star here. This is now the conjugate transpose, or Hermitian. So we will use the star here as the conjugate transpose, or the conjugate depending on if it's a scalar or a vector. But the point is here, this is the way of dealing with complex value data that we will try to run through the course. And it doesn't really make much of a difference, as I noted before, except of course that there will be stars showing up a little here and there. In the case of the autocovariance function, that is the covariance of the p-dimensional stochastic vector with itself, that means index 1 to index 1, index 2 to index 1, and so forth, then I will get a matrix that I will just, first of all, I will just simplify the notation. I'll just say Rx like that. This matrix will always be Hermitian. That is that the matrix is going to be equal to itself conjugate transpose. If it is a real valued matrix, we say it's symmetric, then it's of course just the same thing as saying that Rx is equal to Rx transpose. It will also be positive semi-definite. That means that all the eigenvalues of this covariance matrix are going to be real valued and non-negative. Just as before, we can make the assumption of independence and uncorrelation. And then the difference here would be that if the stochastic vector has independent indices, that means that all the different indices in this vector are independent of each other. There is no relation between one sample to the next. Of course, that is highly unrealistic for the case of the wine sales. As I mentioned before, it's highly unrealistic that you can find variables in reality that are completely independent from each other but of course, in a practical sense, they would be easy to say that they are independent of each other. The uncorrelated would be, the assumption of uncorrelation would be much more useful for us. We will then move the expectations, separate them in to the different stochastic variables like this. One interesting case is the conditional expectation. That is, what if I know something? What can I infer from this on about something else? So, for instance, say that I know the temperature outside. What am I able to say about the precipitation? Or whatever, if I say that I know how many cats there are in my garden, what can I say about the water temperature in Luma? Well, probably not too much. But if I know the Google stock quote, can I say something about the Facebook stock quote? What do I know if I know one thing? And to be able to say, what do I know if I have observed one thing, I use the conditional densities. So that is a probability density saying that what is the density of y if I have observed that x was equal to x naught. That is going to be the joint probability density function divided by the probability density function of this x naught actually occurring, and I can just rewrite it like this. More interesting for us would be the conditional expectation, which is what do you expect to happen on average? And this is exactly what we will use to predict the future. So say, for instance, that I have observed the stock quote of Ericsson for many, many years. That would be my x here, my x naught. That is the stock quote of Ericsson during all these years. And I am curious to see what is going to be the stock quote of Ericsson, well, tomorrow, or what's going to happen on average. So that is going to be a conditional expectation, and that is exactly what I'm going to use to be able to do predictions of the future. To simplify notation, we will often just ignore the given x naught and just say a given x in this way, because of course it can be for any x naught. It doesn't really matter. If they are independent on each other, or then there is no information gained by observing x. So if I do observe the water temperature in Luma, that doesn't tell me too much about the dark side of the moon in practice. That meaning that they are going to be in realistic terms, they're going to be essentially independent of each other. You can also discuss what the conditional covariance matrix is. That is, how much do I expect the different things to vary along time? So if I do make prediction about the future stock quotes, I would be very, very interested in knowing how well I can do that prediction. Say that I can do the prediction of Ericsson. I'll say, it's going to be 100 kroner. That is a completely pointless prediction unless I also tell you how accurate I expect that prediction to be. Is it going to be plus minus 90 kroners? Well, that is relatively pointless. Nobody's going to pay you for that opinion. Whereas if I say plus minus 1 kroner, well, that is information enough for you to be able to trade on it. So this conditional covariance is going to be quite important to be able to say something about it. So that is, what do I know, given that I know x, what do I know about the covariance between the vectors y and z? And this is exactly what we're going to use to be able to determine the quality of our predictions of the future. We might be able to use the variance separation theorem in the cases when it is actually difficult to compute the variance and cross covariances and so forth by hand. So what you do then is that you introduce dependency where there is none. So here you see that I'm looking for the variance of y. What I do is that I introduce knowledge about x, and of course then I take the expected value of all possible x, and in that sense I will average out whatever that x was. So that means that I can describe the variance of y using the conditional expectation here, given the conditional variance of y given z and the conditional expectation of y given x. And same thing, of course, then for the covariance. Here's an example. So if I have the measurement y, that is 8x plus e, where x and e are mutually independent, and a is a real valued constant, and the mean of e is 0, then I can say that the mean of y given x, that is the same thing as moving the expectation in, so that would be the expectation of ax plus e given x. Of course, then ax is known. I mean, if I knew x, I have observed x, so the expectation of ax is going to be, that's just going to be ax. Whereas the expectation of e given x, there is no information gained about the noise since they are independent, so I cannot actually say something about the value of the noise. So the expectation of e given x is going to be exactly the same thing as the expectation of e, and since it was 0, I mean that's going to be 0. The variance of y given x is going to be just e. So because that is notice that it's the variability here is just e, right? I know x. It is already known. So the only thing that is unknown is going to be x. The other thing is just the scaling. So the variance of y given x is going to be the variance of e. Similarly, then I can use this variance separation theorem, and I'll just rewrite the expected value of y, and I'll use then the expected value of the expected value of y given x, and I just computed this to be ax, right? So that means that the expected value of y is going to be a going to the expected value of x. Same thing for the variance. I can use the variance separation theorem and say, well, what is the expected value of the variance, and then the variance of the expected value, and I'll get the variance of the noise plus the 8 squared times the variance of the x.